in previous lecture, we've been talking about parametric equation, okay, for curves in 3D space. The focus is on how to properly find the parametric equation for some common functions, for some common curves, like a circle, ellipse, like a regular scalar function, or straight lines in 3D space. Okay, so you need to be able to construct those, okay, for our future operations. Now today we're going to looking at this. What's this? So today we're going to look at vector function out here and their operations. Basically, we're looking at vector function. We're looking at derivative, integral, and some concept related to vector functions. Okay. First of all, let's look at the definition of vector function. So we actually already talked about the vector function when we parameterized some 3D curves. Okay. So let's say this is a curve in 3D space. Okay. And we're using its position vector to represent its time history. Okay. So this is a position vector. We have been using it, okay, to represent its trajectory. Okay. So the definition is actually pretty simple. Okay. If we have this position vector, okay, so which is a function of t, okay, yeah, and this r of t, okay, defines basically, r of t is defined, okay, for t belong to certain range. Let's say a to b, okay, yeah. Then this r of t, okay, is a so-called vector, okay, function. Okay, yeah, it's a so-called vector function. So what's the difference between this vector function and a regular function that you learned in the first year is basically those are what we call the scalar function. Okay, make sure you know the difference. So when you look at scalar function, for example, okay, we have f of x. That's a scalar function. And in the next week, we're going to look at the multivariable function. So let's just know f, x, y, z. Okay, that's a multivariable function. But this is also a scalar function. Okay, yeah. So scalar function, when you substitute a certain values x, y, z, or x into its function, you're going to get a scalar value, right, out of this function here. But if it's a vector function, when you substitute a value for the t, what's returned is giving you a vector. Okay, that's basically the idea here. Okay, yeah. And the other point is also you should always remember is r of t here. We call it vector function here. If it's just making if it's more easily to understand, you can you can think of it as basically a position vector. Okay. It's a position vector. Okay, so now let's look at some operations regarding this vector function here. Okay, so in the scalar function, we have learned derivative integrals. So we have a similar operations regarding vector function. So the first thing, let's look at is a derivative. Okay. Derivative vector function. Okay. Yeah. Okay. So just like a scalar function, we do have a very similar, very similar definition as the scalar function. So first of all, okay, let's look at the definition of a derivative here. Okay. So let's just say it's the same notation that we used as above here. Then the derivative of this vector function, okay, this derivative is defined as this. it's a limit, okay, and taking very small delta t go to 0, and then you have a small incremental, okay, t plus delta t at here, okay, and minus, okay, the r of t and over delta t. So that's the definition at here. So if I draw a diagram just for illustration at here, so let's just say I have a curve at here, okay. Then if this is at the t location, okay, so you have one position vector. So let's say this is r of t, okay, r of t. And if this is after delta t time, okay, and this is r vector t plus delta t, okay, so after delta t interval, okay, and let's say this is a, b locations, right? Yeah. Then we can form a triangle, okay, and basically, okay, form a triangle right here, so vector addition and subtraction. So this portion at here, right, this portion essentially is the numerator at here, right, the numerator, okay. So we can call that, let's say, delta r of t, something like that, right, yeah. Okay. So apparently, you see, the limit is basically, instead of a bigger delta t, if we have a small delta t, then a b will be infinitely approaching this location a at here, right? Yeah, and then you get your derivative. It's the same. It's basically the same kind of a derivative definition. The scalar, right? If you change the r to f, that's a scalar function. Okay. Now, as a matter of fact, when you look at the way that the definition of this derivative vector function defined, this is a derivative. So this vector, okay, this vector right here, as it goes, okay, as it is at delta t approaches to 0. So as you can see, the end results of the derivative of the vector function give you another vector function, right? Give you another vector function, and this vector function is actually going to be tangent to the curve, okay, you are looking at here. Okay, so this is the tangent, okay, to the curve. Okay, tangent to the curve. So, in terms of the calculation, it's actually pretty simple. I mean, let's just say, in general, if our x of t, if our position vector or a vector function r of t is this, okay, then if we're going to take the derivative of this vector function, so what do? We basically actually just doing it separately for each one of them in here, right? So dr over dt, okay. So dr over dt essentially equal to, okay, dx over dt I hat plus dy over dt and g hat plus dz over dt and k hat. Okay, so that's how you carry out the specific operations. So do we know how to do this? Yes, right? So just combine them together. That's the derivative of vector function. Okay? Yeah. So as a matter of fact, as you can see some exercises here, most of the time it's a sort of a recollection of our old yeah, go ahead.
When you use Spanish, how come only the y you're taking with respect to time?
Sorry, come again?
So it's dy t.
Oh, you mean I didn't write this one here?
Yeah.
Oh, that's okay. Yeah. So yeah, you can neglect the bracket here. That just means it's a function of t. If you don't write it here, then by default you know that x is a function of t, right? Yeah. So that doesn't have to be there. Okay? Yeah. Of course, if you want it to be more specific, you can write it like this. That's fine. Okay? Yeah. Okay. So let's do a very simple exercise. So this is a parametric equation that we've seen it in the previous lecture. Okay, it's what we call the helical or helix, right? It just this portion is slightly different from the previous one. There's just basically give you a different pitch, right? From the different spirals. So in this case, let's see. I'm going to calculate, okay, the derivative of this vector function. So you can write dr, or you can write dr of t. Okay, that's fine. Okay, it doesn't matter. Okay. So because this is pretty simple, so all you need to do is just calculate the derivative of each of these components that are here. Okay, so I think this is basically a time to revisit many of the basic operations here. So derivative of cosine give us what? Sine. And derivative of sine give us a cosine. And derivative of this give us 2tk. Right? That's it. Okay. So now if I relate this mathematical expression to a certain kind of physical meaning now, R of t, remember I called it position vector, right? Basically represent the position of a certain point in the 3D space. And derivative position, so naturally should give us velocity, right? So I should give a velocity here. So we don't call it speed though, huh? So speed is a scalar quantity. So velocity is a vector quantity. So what I need is an acceleration. So then what do? We basically take another derivative with respect to this velocity here, right? Yeah. So if you go one step backwards here, that's basically taking second order derivative of the original position vector, right? Okay. Yeah. So that's acceleration. So velocity, basically this represents it's the velocity. So this is a helical curve, right? Something like this. Okay. So that basically represents the velocity which is tangent to the curve, okay, at a certain point along the helical curve. Okay. So if I do one more step of a derivative here, so you're taking derivative based on the new expression in here now, right? So sine is the cosine. Derivative of that is cosine. Derivative of cosine is negative sine. So that's minus 3 sine t, okay, g hat, plus 2 k hat. Okay, yeah. So that's acceleration. Okay. And often in time, particularly as you see in the next shortly, okay, what we need is we're going to normalize this velocity, okay, to get a so-called tangent vector. So if I normalize this one, basically I want to get a norm of this, and that in terms of the physics, that's what we call the speed now, right? The speed. Okay. So let's just say for this particular here, if I normalize that, what will be the norm? Square of this quantity plus the square of this and plus the square of this, right? Yeah. So the square of this is 9 sine t squared. The square of this is 9 cosine t squared. And guess what? When you add them together, which equal to 1. So what's the trigonometry identity applied to the first two terms? Anybody? Huh? So what is sine squared plus cosine squared equal to? 1. So basically the first two terms end up with 9, right? Yeah. And plus 4t squared. Okay? Yeah. Yeah, this is another thing I often emphasize here. So some of the basic trig identity you will have to remember. Particularly, it has to be. Okay? Okay, so in this particular case, can you examine? Okay, can you examine what is the relationship between the velocity and acceleration at here? Essentially, what's the geometry relationship between the velocity and acceleration? So what do we do to examine the geometry relationship? What we do is we can do a dot product here, right? Can do a dot product. So if I carry out a dot product, it's basically the dot product of this vector with the dot product with this vector here. Okay? Yeah. So as you can see, what's the first two? This is a -3 sine, -3 cosine. So that's 9 cosine sine. And the second one here is positive, right? And the second one here is positive, -9, and it's cosine sine. So when you add the two terms together, they're actually going to be 0. So only left with is a 4t at here, right? It's 4t. Okay? So 4t, yeah.
Where did the 4t squared come from?
This one?
Yeah.
We're looking at this norm of this magnitude of this vector here, right?
Yeah.
Magnitude of this vector is the square root of square of this plus square of this plus square of this. So that's where it's from. Okay. So back to here. So dot product of these two is 4t. It doesn't seem to be very significant, but what happens is at t equal to 0, and this term is 0. So at t equal to 0 is 0. So that means these two vectors actually are perpendicular to each other. Okay? Yeah. Okay. So that's derivative. Okay, that's derivative. And for scalar function, when we are taking derivative, and then naturally we examine the two very common properties, which is called basically product rule and the quotient rules, something like that, right? So we have very similar rules associated with the vectors. Okay, so I'll write down some of the very common ones here. First, let's look at the product rule. Okay. Now the reality is this is not the multiplication of two scalar function. This is we're talking about multiplication of two vector function. Now when we say multiplication of a two vector function, we actually talking about two different multiplication. One is a dot product, the other is cross product, right? Yeah. So that's the multiplication applied to vectors. So you actually do have a product rule applied to dot product type of things and cross product. So this is the dot product. Okay, this dot product. In terms of similarity, it's the same thing. Okay, it's the same thing. So this is a two products, two vector. It's dot product. And then this is a u prime of t. So prime also referred to derivative, right? So there are different ways. Usually what I generally see in other courses, there are three ways of writing derivative. Basically as well. One is y prime, y dot, and the dy over, let's say y is a function of x, okay, and dx, right? There's three ways of writing derivatives, okay? Yeah. So in this case, it's not multiplication because it's dot product, so it's dot product here, okay? Yeah, and u dot v prime, okay, t. Okay. Each notation actually has a different names, okay? That's dot product. Okay, so you could also have a cross product. Okay, okay. So when you expand this one using product rule, okay, so just change this dot into a cross product here. Okay. Okay. Yeah. So this is very important. Okay. This is basically sometimes when you carry out a derivative action, which is not just the one vector function, but some mixed together. This is the rule you need to follow. Okay. Yeah. And there's also this chain rule, okay, that's very commonly used in scalar function, as we're going to see in the exercise following here. So chain rule is supposed like this. So let's just say it's this, okay? Given maybe what we have is a vector u, okay, and u is a function, okay, u vector function of x, okay. At the same time, the x, okay, is a function of t. Okay? So then the du, okay. So this du of x over dt, okay. So this one here, okay. And that is the chain rule following here. Oh, and by the way, sometimes you probably will see me in the lecture notes or in somewhere, when I write this derivative, okay, in order to have a less confusion, I actually sometimes write like this. Okay, particularly if I'm taking derivative along expressions. Okay, so basically taking derivative whatever inside the brackets at here. Right? Yeah. So, chain rule. So what does that mean? That means you take the du vector, okay, with respect to x first, okay, to x first. And then the x is function of a t, so then x with respect to t. Okay, so that's the chain rule here. So to simplify the writing a little bit, and we sometimes use this notation at here, okay, to represent this dx over dt. So this notation, x note, I think that I remember that's called Newton's notation. That's usually applied to the function, to a function which is a function of a t, a time function. Okay, yeah, x dot. So x dot is this. Okay. So I think the exercise is actually you can exercise yourself. This is pretty simple right here. Okay, I'm not gonna probably. I'll just write it here. So t squared -3 and v t. Okay. So let's say you have two vectors like this, and you are required to calculate the derivative of the dot product, okay, of these two vectors. Okay, yeah. So chain rule, a product rule, right? So like this, okay. So you can take derivative of this first, dot that, plus this, dot derivative of this one, right? Yeah. As a matter of fact, you can also do another way, which is what? You do the dot product first and then derivative, right? Then you don't need the product rule anymore, right? Yeah. But anyhow, test it to try it out yourself either way, okay? And you get this. Okay, it's pretty simple. Okay. Any questions? No good? Okay. So now let's take a look at another example here. This is a sort of interesting one here. Okay. This is very much related to particle motion. Okay. So let's say you have a particle. Okay. Let's say you have a particle which is constrained to the circle at here. Okay, so the circle has a certain radius, of course. Okay, so let's just say the circle. If I represent the position vector using r at here, so that's r of t position vector, and it's going to be moving along this circle here, right? Rotation motion. Okay, so as you learned in your first year dynamics, the velocity of this motion is actually what? It's actually tangent to the circle, right? Yeah. So here's a simple proof why the velocity is tangent to the trajectory or the circle. Okay, when you have a constant, basically radius at here. So it's a constant radius. That basically means this r of t equal to a constant here, right? So let's just say circular motion. Okay, circular motion. So it's a constant, a certain radius. Now let's manipulate this guy at here. This one represents the magnitude of this vector. Now if you remember when we learned dot product, the magnitude essentially of I'll do this. So if I do a square of this, right, it's still a constant, right? Still a constant. Okay? So what's the square of this one here? It's actually, was that right? Yeah, it's a dot product, right? So of course, or square root of this give you back the magnitude. Okay? Yeah. So this guy equal to this. So that equal to let's say c square. Okay? C square. Okay. So now what I'm going to do is I'm going to take a derivative, okay, of both sides of this equation or this equation here with respect to t. Okay? So take derivative, okay, of both sides. Okay, so taking derivative of both sides meaning you taking derivative like this, right? So this is a constant. So the constant derivative basically 0. Okay, and then this side here, and that's the kind of a product rule, right? We can make use of because there are two vectors dot each other at here, right? Yeah. So apply the product rule, which give us this one, r prime of t dot what? R of t. And then plus r of t dot the second one prime, right? Equal to 0. Okay? Yeah. Was that clear? Yeah. So dot product is a commutative. So basically A dot B equal to B dot A, but not cross product. Okay? So this basically means this side here is 2. R of t dot R prime of t equal to 0. Or you can get rid of the 2, right? Divided by 2 each side because this side is 0. So you get what? You get R of t dot R prime of t equal to 0. So what does that tell you? What's the geometric relation between R of t and R prime of t? They are perpendicular, right? And R prime of t is actually what we're looking for, is basically the velocity, right? The velocity here. So this is the velocity here. Okay? Velocity. So this basically proves the circular motion, the velocity, right, giving a constant position vector, okay, constant magnitude for the position vector, and then the velocity is perpendicular to the position vector. Okay? Yeah. We're going to make use of this. Actually, we're going to make use of this observation shortly here. Okay? Shortly. Okay. Okay. So that's derivative. Okay. That's derivative. Okay. 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 So now let's look at integrals. Okay. Integration of vector function. Okay. Integration vector function. Okay. So integration vector function, I will still use the same kind of notation as I used as above there. Okay. So now we are going to integrate this integral. So when you do integrate, we know that there are two different integrals. One is there's a definite integral or indefinite integral. So let's just say use this one here. Integration, okay, of this r of t here. So very simple. Okay, instead of integrate this one, what you need to end up with integral, doing integral for each one of the component at here. So integration of this one integration of this one, and integration of this one. Okay? Yeah. However, it is a pitfall in here, and don't forget what? Plus C. Who wouldn't approve this? Well, I guess we all know that a scalar function give us a C here, right? But now we're dealing with a vector function. So this is a constant. This is a vector function. Instead of a constant, it's actually going to be a constant vector. Okay? That's beautiful here. Because just as this scalar function here, the derivative of this capital F of x, right, this is called antiderivative. Derivative of this, or derivative of the right side, should give you back this small f of x. So the derivative of this whole thing here should give you back this one here. Okay? Yeah. Okay, so yes.
For like if you're going back and you have a C value, will
Yeah.
the C like have all three coordinates with it?
Yes.
Yeah.
Constant though, right?
Yeah.
That's right. So C1, C2, C3, like this. Yeah. Good. So you can call this portion, right? You can call this portion just like this capital F of x. You can call this portion as another vector function. That's basically the antiderivative, right? The antiderivative. Okay. Okay. Antiderivative vector function. Okay. Okay. So you can try just very quickly an example out of here. Okay, so here is my vector function. Okay, what will be the integral of this one and here? Okay, will be the integral. So be aware of that pitfall. Okay, very simple. And all you need to do is to carry out the integral for each one of the components, right? For each one of the component. So the integral of the first one is t squared. Second one, t. And third, t cubed. Okay, t cubed. So, and then don't forget, plus the constant c. Okay? Yeah. Is that okay? Yeah. So that's how you do the integral. Unless you're integrating, giving a limit set here. Okay? If you're giving limits, forget about the c, right? Yeah, you don't need that anymore. Okay? Yeah. Okay, so now here comes the more general or interesting stuff. Okay? So let's look at a couple of concepts here related to this derivative particularly. Okay, so we're looking at as a tangent vector, unit tangent. So we're going to look at each one here. Unit tangent vector. Okay, and also particular unit normal. Okay, binormal. Okay, yeah. So, what are each one of them? Okay, and how we'll show that through an example. Okay. So first of all, let's illustrate this one. Tangent vector. Actually, we already did that. So if I have a curve, okay, in the 3D space, and this is my position vector at here, then at that particular point, you calculate, okay, the derivative of this r of t. That's basically a tangent vector. Okay, it's basically tangent vector. Okay, so that's pretty straightforward. Okay. So tangent vector in terms of the formula, just like we write before, is dx over dt, dy over dt, and dz over dt. Okay, yes, tangent vector. Okay, so what's making it a little more sophisticated or complex is the next one. So we're going to get the unit one, unit tangent vector. All right? Yeah. So by the name of the unit tangent vector, I think it's pretty simple. Unit tangent vector, basically, you're going to normalize this tangent vector, right? To make what? To make the lengths to be 1. Okay? So unit tangent vector. Okay? Unit tangent vector. So unit tangent vector, we always use a hat, right, symbol to represent unit vector. So that's the unit tangent vector. So it's still going to be a function of t. Okay. All we need is just need to normalize that. Okay, and that gives us a unit tangent vector. Okay. Yeah. So if you want to express the unit tangent vector using original vector function r of t, so r of t is derivative that gives you a tangent vector. So we can use this r prime here to represent this d over dt. Okay, so it's a unit tangent vector. Yeah. There is an alternative formula for unit tangent vector. Okay, so basically, you look at what we have been talking about is we're always saying the position vector is of time is a function of t. So at a different t, you are at a different location here, right? Different location. And r of t essentially is a parametric equation: x of t, y of t, z of t, right? Yeah. So there is also a possibility, okay, that instead of using, let's say, t for the parametric equation, we can use, we can use the arc length as a parameter for the parametric equation. So arc length meaning, let's say you start at here, right? You start here. Then after a certain time, it travels here. So that's the arc length we're talking. How much length that has traveled? What's the displacement? What the distance has it traveled along the curve? That's arc length, right? Yeah. So arc length is sometimes actually making more sense, particularly if you're talking about speed, right? So you have a roller coaster is moving. So you say, oh, how fast is it moving, right? So you can say, oh, okay, look, in 1 second it travels this much of arc length. So that is faster, and if you travel this much, then it's faster, right? So that's basically the possibility here. So we can also use for this r of t, okay, let's say for r for curve, right? For the curve, okay, we can use the so-called r of s. Okay, so s that here is the arc length to represent this curve c here. Okay, represent the curve c. Okay, and s is the arc length. Okay, s is arc length. So if this is the case that here, so let me show you an expression here. Okay, so I'm going to instead of taking r, okay, over the t, so now we're going to take a derivative r over s. Probably in the next lecture, I'll show you an example where can we get a parametric equation for a curve using arc length s instead of t. Okay, so for now, just trust me. Usually, r of s is not as popular as r of t. Okay, so it's not as easy to find as r of t. So here, I'm going to use the chain rule at here. Okay, a chain rule. So this is arc length s, and guess what? Arc length s actually could be a function of time t. Okay, so if I take dr over ds, so I can do this. I can do dr over dt first. Okay, dr over dt. So just simply to get rid of the dt, I can put the dt over here and ds over here, right? ds over here. So you can get rid of these two. Okay, get rid of these two. You can cancel. Now I'll manipulate this portion slightly. I'll move this dt to the denominator. So what do I get? Right, I get this 1 over dt over ds, right? ds over dt. Okay. So ds over dt, s is, remember what s is. S is arc length or the displacement, right? Okay, displacement. So physics, ds over dt give us not velocity, not the position. Remember what you call that? Speed, right? Speed. So it gives us a speed, and speed is actually what quantity of the velocity? Scalar quantity. So that's basically, this is 1 over the magnitude of the velocity, right? Magnitude of velocity. Okay? Yeah. So now if you compare this, the end results of this portion right here with this one, look at that. What did you see? They are actually, are they the same? Yeah, right? They are the same. Yeah, the bottom here I'm writing r prime, but r prime is velocity, right? Yeah. So that means this quantity give us the t hat, right? T hat. So now you see the difference here now, right? So t hat, okay, is this. That's in terms of t, right? If you happen to have r of s in terms of arc length, your t hat is actually just simply dr over ds. Okay? So in other words, this dr over dt is not the same as dr over ds. Okay? dr over ds. Although that r of t or r of s, the two vector functions probably refer to the same curve C. Okay? Same curve C. Okay? Yeah. Is that okay? Yeah. Okay, so that's unit tangent vector, right? That's unit tangent vector. So now let's look at another special one called the unit normal vector. Okay? More precisely, we call that principal, okay, unit, okay, normal vector. Okay, principal unit normal vector. So this is a vector that is perpendicular to the t hat. Okay, to the t hat. So you have a curve, and this is a t hat. Okay, this is t hat. Or somewhere here you have another t hat. Okay. So technically speaking, giving a curve in 3D space, how many perpendicular vector is there to this t hat? How many in 3D space? You have infinite, right? Yeah. But there is one special one, and that one is indication. It's we call that principal unit normal vector. It indicates where or what direction the curve is turning. Okay, that's the special one here. Okay, so we're basically looking at this guy here, the n hat. Okay, so this is what we call this principal unit normal vector n hat. And n hat, I'll give you the meaning here. N hat basically an indication is the direction direction where the curve is turning. Okay, where the curve is turning. So instead of, I'll show it through different steps here. Okay, instead of getting n hat directly, I give you n hat directly. I'll give you what, not n hat, I'll tell you what this n vector is, okay? Yeah, what the n vector is, and then where the n vector is from. And then we'll end up with this n hat, okay? Yeah. So, let's do this. We're basically starting from this t hat at here. Remember what t hat is? That's a unit normal. That's a unit tangent vector, right? Unit tangent vector meaning what's the magnitude? It's equal to 1. So, or it's a constant. So if it's a constant, as example here shows at here. What example? Here, right? When the vector has a constant magnitude, basically the derivative of the vector is perpendicular to itself, right? Perpendicular to itself. So basically, coming back here, dt hat over dt is actually perpendicular to t hat, right? It's perpendicular to t hat. Okay? So this one here, okay, is actually our n vector. Okay? Is actually our n vector. So I'll show you slightly different explanation here. Okay, so then why dt hat over dt represent essentially n is the same direction n hat. Why does it represent the direction the curve is turning here, right? So you can think of it like this, okay? So for example, this is a moment at the t at this one. This is a t hat here. If I draw my curve here, let's say at this location, and this is another t hat. So let's say this is a t here, and this is t plus delta t. Is that okay, right? It's t plus delta t here. Okay? So these two vectors, if you move these two vectors together, so this is a t, and this, okay, and this is a t hat, okay, at t, and this is t hat, t plus delta t, okay, yeah. So then I can have a very small vector constructed from these two at here, okay, very small vector constructed from here. And for this particular one at here, okay, that's actually according to the derivative definition. Remember derivative definition as well. If I do a limit, okay, t, okay, so t hat minus this guy at here, right? T minus this, that's this vector, right? That's this vector. If I take a derivative now, if I take a limit now, letting delta t equal to 0, right? So according to the definition, what's this one? That's actually, right, the derivative of this t hat, right? Derivative t hat, okay? So if you look at the illustration here, where is that direction of this small segment here, this small segment vector here? It's pointing to the direction where the curve is turning, okay? Yeah. So that's indicated by the direction of the turning is indicated basically related to the direction where this tangent vector is going, right? Tangent vector this way, this time this, the next moment is that way, right? That means there's also the turn in the curve must be this direction here, right? Yeah. Okay? Yeah. But you got to be careful, okay? This is not a unit normal vector, not the principal unit normal vector. This is just a vector here, okay? So even though this is a unit vector, so derivative of a unit vector not necessarily give you another unit vector. Okay, that's very important things. Many mistakes happens over here. So what that means is, if I need n hat, okay, if I need n hat, what do I need to do? Exactly, I need to normalize this guy. Okay, so if I plug everything into it, that basically gives me dt hat over dt, that's n vector, and divided by its length. Okay, divided by its length. Okay, that's n hat. Okay, that's n hat. So when we describe a motion of particle along certain trajectory, often in time we need this the two vectors. Okay, sometimes we need to decompose a certain vector into these two directions. Okay, to describe it. Okay, so the last vector, which is called binomial vector, okay, and this is defined as this. Okay, B hat equal to T hat cross N hat. Okay, cross N hat. Okay, so what does that mean if I go back to this curve right here? So this is T, this is N. If you do a cross product T cross N, where does it go? Actually, it goes into the page, right? Into the page. Okay, for this location right here. Okay, for this location, T cross N goes into the page. Okay. How about this location here? First of all, where's the N hat direction should be? Yeah, right? Then N and then T cross N, the B is out of the page here, right? Out of the page. Okay, right hand rule. Okay? Now, what's the relationship when you have x, y, z coordinates? Yeah, you have x, y, z coordinates, and we often saying this is I hat, this is J hat direction, and this is K hat, right? This is K hat. When you construct a Cartesian coordinates, it always satisfies what rule? Right hand rule, right? So x cross y or I cross j give you the k, right? And k cross I give you the y. Okay, so basically it's always satisfy this right hand rule here. So then, based on the current definition of a unit tangent vector, unit normal vector, n hat, principal unit normal vector, and the binomial vector. So we actually able to construct a so-called TNB frame. Okay, TNB frame. So this it's like X, Y, Z frame, but not necessarily. Okay, not necessarily. This has to be X. This has to be Y, but it's TNB frame. Okay, so T cross N give you B. Okay. N cross B and give you N, like that. Okay. So there's also a more sophisticated name given based on two mathematicians. Okay, it's called Freenet. I'm not sure even Serret frame, something like that. Okay, yeah. Serret, yeah. So based on two names. Okay, it's the same thing. Okay. This is actually turned out to be a very useful frame. Okay, very useful frame. So why is it useful is this. So let's just say you have a certain trajectory, right, in the 3D space. For example, you have, as we illustrated, let's say you have a helical curves trajectory. Then based on the trajectory at any location, you can construct what? You can construct a T, right, unit tangent vector at the location. You can also construct N, so this is T hat, this is N hat, and then there's also a B hat, okay, right. So basically you can attach a TNB frame for a particle moving along this trajectory. Does that make sense? Right? So imagine this, right? Imagine this. If the particle is moving, so that this frame, this is basically a TNB frame, or this is basically a coordinate system. So this coordinate system is actually not going to be a constant, right? It's actually going to go through certain kind of rotations. Is that right? Yeah. So now imagine this, right? If I have a robot, and my robot has a certain two frames that are here. So what I want is, I want my robot basically to not just follow the trajectory here, right? So the robot is going to follow the trajectory, but also I want the tool frame to follow certain orientation. For example, to follow this TNB frames. Okay? You visualize that, right? That's actually important. Sometimes when you do when you do the robot's supposed to do some kind of a painting or a deburring or that kind of work. So the robot has to basically move its hand to adapt to the surface that it's working on, right? So this is basically a typical application. What we call there's a position. There's also so-called orientation. So two things need to be satisfied to describe the motion of a robot here, right? Then, of course, the number one step, we have to calculate what is the TNB frame based on the given trajectory, right? So we have to calculate TNB frame. So what do you mean by calculating TNB frame? We have to calculate T hat, N hat, and B hat, right? And then we'll give it to the robot. And the robot will follow TNB. Is that good? And that's actually one of in the fourth year, you will learn some of this here. I'll show you one of the projects students will do in the robotics course, right? So this is a so-called Puma robot, and there is any factor. So there's a frame attached to any factor. So that frame, according to required, needs to follow the TNB frame, okay, as it goes along the trajectory here. So this is essentially involving forward kinematics and inverse kinematics, right? But the first step that it has to do is to get the information of T hat, N hat, and B hat. Okay, that's the foundation. Is that clear? Okay, so now back to this question here now. So, let's look at an example, calculating T hat, N hat, and B hat. All right? Yeah. So this example, in the past, I have seen a puzzle, okay, lots of students here. Puzzle meaning it's actually not difficult, but you just can't get the result. Here is a vector function or position vector, okay? And I want you to obtain the T hat and N hat. Okay, once you obtain the T hat and N hat. Okay, so your initial look at this question is actually, well, that doesn't seem to be very difficult. Okay, it's a pretty simple vector function. But trust me, as it goes on, you'll see some difficulties here. Okay. So I'll do the easy part, and then you can start the difficult part. First, we need the T hat, but we have to calculate T vector first, right? Yeah. So let's try the easy part. Yeah. So that's dr over dt, which is 2t, I'll just write 2t, 3, 0. Okay? Yeah. And then T hat. Okay, T hat. To normalize this vector, okay, by its magnitude. And the vector itself is like this, so nothing changed. Magnitude, which is 1 over this magnitude, which is what? Square root 4t squared plus 9, right? Plus 9, okay? So you can multiply this into the bracket, that's fine, but since it's a common one, so you can take it out of the bracket. So 1 over this, right? Okay? Okay, so now the next one is, I want you to do this now, okay? What will be the N hat? So you look at the formula here, N hat equal to what? This guy divided by this magnitude. So what we need to do is we need to calculate the derivative of a dt hat over dt, right? So we need to calculate this first. So let's calculate this guy here. Okay? Yeah, so I'll give you some time. I actually want you to practice this before I try it out here, okay? This is actually not going to be a new, this is what you learn in the first year, but I find that lots of people couldn't finish. Okay? Yeah, so do try it though, do try it. So dt hat over dt, in other words, according to the derivative of a vector function, it basically means what? You're taking derivative of x of t. X of t is 2t over this. And y of t is 3 over this, right? And the third one is 0. Okay? So the question is, what's the derivative of this one? And what is the derivative of this one here? Okay? So I'll give you some time. It's a couple minutes, a few minutes here. See if you can figure out the derivative of this two here. Or maybe just work on one here. Okay? If you know how to do one, then you go get for the other one. Okay, so 5 minutes, almost 5 minutes, right? Well, I'm walking around. I haven't seen anybody got the answer yet, but for sure, just like previous years, it seems to be a difficult derivative to calculate, right? Yeah. But lots of people started thinking in the right direction, okay, using quotient rules. Okay, so that's good. Okay. As I kept saying, one of the courses I often emphasize that in this course is one of the things I emphasize is the calculation skill. Okay, yeah. Of course, if you plug it into the Maple or any other software, you get the results, right? But I need you to be able to calculate some of these derivatives, particularly in the multivariable function. When we do partial derivatives, right? This is going to come back again. Okay, so I'm going to calculate the first one in here. Okay. First one. All right, so in this case, what's u? U is 2t, right? What's v? V is this portion. Okay? So v squared give us 4t squared plus 9. Okay? U prime, maybe I'll just write it. U is this, v is this. So u prime is derivative of 2t with respect to t, which means this is 2, right? Times v times this. Okay? And u, again, u is 2t, times v prime. Okay, so this is where lots of weird things going to happen here. V is this. What is the derivative of this guy here? So v prime, or in other words, what's dv over dt? In other words, what's d over dt? 4t squared plus 9. If you don't like if you don't like square root, you can write it as what? 1/2, right? Okay, that's what happens here. So what is the derivative of this one? If you're not comfortable with this, you can apply a so-called chain rule. So you can let what? You can let, let's say, w equal to 4t squared plus 9. Is that okay, right? Then the derivative of this one is to take the derivatives with respect to the w first, and then derivative w with respect to t. Well, no, sorry. d of w 1 over 2, 1 to the power 1 over 2, and then dw over dt. Does that make sense? Yeah. So, what is the first derivative here, which is what? 1/2 w to the power of
Negative 1/2.
That's right. And dw over dt, what is w? It's this. So that gives us
8t.
Yeah. Excellent. Sound this week. Yeah, you should give him applause actually. So that's good. So coming back here, plug w back here, right? Plug it back here. And move it to here. So what do we get? 1/2. W is 4t squared plus 9, but this is negative 1/2. And multiply by 8t. Okay? Was that right? Yeah. Okay? Yeah. Okay, so this is now the next step. It actually has nothing to do with university now. It's high school. Because there's no derivative, no integrals, right? The next is actually the simplification of polynomials. However, it is a little bit tricky because you got all of the squares, negative, positive things here, and often in time in exam, I see lots of students just leave it like that. Here you are, go simplify for me yourself. But the problem is, if I ask you to do one more derivative based on this one, right? That's impossible to do without simplification first. Okay? Yeah. So you have to simplify this expression first. All right? Let's just see, how do I simplify? These two cancel this 1/2 out here, right? Cancel this 1/2. Okay? And this one here is 4t squared 9, negative 1 over 2. So I'm going to do this. So 2 out of here, 4t squared over 9. So t, I think I'm going to I like to write it like this way. So this is negative 1 over 2. So which means this is 1 over what? Was that okay? Right? And times the 8t and 8t here, right? 8t. Okay? Times 8t. That make sense? Yeah? And divided by 4t squared plus 9. Okay? So over here, this is where you need to do some simplification. So I'll move the t over here, so it's 8t squared. Okay? 8t squared. Okay? Then this is like this, right? And a minus 1 over b and something, right? 1 over b. So how do I simplify the numerator? This is basically ab minus 1 over b, right? Okay? So you look at this one here. So simplify this as this times this. Now this times this give us 2 times, right? And minus what? 8t squared. And over what? Okay? Is everybody following here? Yeah? Okay. So don't forget the original denominator here. Okay? So now look at this. This is x over y over z. And what is that equal to?
X over y max 1.
Yes, yes. But trust me, I have seen so many times a student do this. This equal to zx over y. Okay? Yeah. So if you make this mistake, don't expect me to forgive you though. Okay? Yeah. So, which means I'm going to multiply this with this, right? Multiply this with this. And how do you simplify these two multiplications? They are actually what? Was that right? Yeah. And here, expanded 2 times 4t squared plus 18 minus 8t squared, which is 18, right? You see that? This is so simpler, right? So much simpler than this step here. Okay? Yeah. Now this is what I'm talking about here. You need to be able to do this though, huh? You need to be able to do this. Okay? So very much chances that you will have this kind of derivatives things in the exam. Okay, so what is this again? This is dt hat over dt, right? No, only a part of that, sorry. This is only part of that, okay? So you can try the other part, okay? And then you will get a dt hat over dt. So I'll write it down here, okay? So dt hat over dt is this portion. This is I hat, okay? The other portion is this. Okay, is this. So they all have the same denominator, okay? They all have the same denominator, okay? And this. Okay? And guess what? Then the next step again is a tricky one. So you need to calculate the magnitude of this one here, right? And just looking at this, you probably, right? Yeah, just looks are going to be ugly. But trust me, a lot of time, many things can be simplified. So don't be scared by the initial look, okay? You can do a little simplifications first. To 12, 18, there's a 6, right, as a common. And this is 4t squared plus 9, and that's a common one. So inside here is 3i minus 2t. Not just 3i, just 3 negative 2t, right? That's this one here. So when you're taking magnitude of this vector, so since this is a common things, it's like this, right? It's like a 3 times 2, 3. What's the magnitude? It's again, 3 will be outside here, and then 2 squared plus 3 squares. Okay, like this. Okay. So you will have this one showing up at here. Okay, and then you calculate the 9 plus 4t squared. So 9 plus 4t squared. See, look at that, right? So you have a 4t squared plus 9, 3 over 2. You have square root of this. What's the simplification? Cancel? No, there's a 3 over 2 here, right? Yeah, so how, but yes, you will cancel something here, right? So what would be the results then? 6 over what?
Power 1.
Or in other words, how do you do if this is too much, maybe how about a 3 over 2 over this guy here? This is what? a 1 over 2, right? And how do you simplify it? This 6 over 8, exactly. Okay, yeah. So anyhow, I think the rest of the work are pretty mechanically, calculation just by following the steps here, right? Yeah. But right, this is a skill, needs practice though. Any questions? Okay, okay. Okay.